So let's get started, and I'll introduce myself. So I'm Roshan. I'm a PhD student working with Shaba. Shaba is still in Hungary having fun biking, so I'm talking about some slightly off-the-wall stuff today. So I know the topic of this course is reasoning for LLMs, and so we've been talking a lot about formal languages and what LLMs can do with formal languages. But let's take a look at a slightly different topic, which is we talked about all of these results in learning theory. We know that humans learn languages, right? So humans learn natural languages. So based on this, what does learning theory tell us about humans, and what does learning theory tell us about natural languages? So my talk today is mostly going to be a summarization of this paper in the reading list by Osherson et al. From 1984. I'll just write that down here. And there'll also be like little bits from other papers by Gold and Anglin, and I'll highlight those as they come up. Okay, so like I said, the idea is that we know that human children learn languages, and they can learn natural languages, right? So imagine that we've created this set of the natural languages, and really we don't have a definition of what a natural language is, except it's the languages that humans learn, right? So we're just going to go with that. And we call H human learner. And you should think of the human learner as like a child who's learning their first language, right? So in the paper they talk about it like a 3-year-old child, right? And before we get started with any theory, we need to immediately formalize a few things, right? We need to say what exactly is a natural language, what is a language, what's a learner, etc. Right? So in 1981, Mark Gold suggested this framework called language learning theory. And that is the framework in which all of this work it happens. And so let's introduce what this framework is, right? So what is a language first? So a language is a set of sentences. And what is a sentence? So sentences are just like what you think of as sentences, right? So like English sentences. But the important thing is that it's going to be a countable number, right? So you can think of that as sentence number 1, a sentence number 2, etc. Right? And the ordering doesn't really matter. What matters is that every sentence has a number, right? So I just say here, sentence is a number. And what this actually means is that there is some way of encoding every sentence, and then there is some rule that for any given number gives you a sentence, right? So this sounds really weird if I write it down, but hopefully that makes sense. And these are going to be sentences in all possible languages, right? So we're going to have one numbering scheme for every possible sentence that you can see, right? And so that means a language is just going to be a subset of the natural numbers, right? So simple enough. Okay. And yeah.
The language is finite, right? It can't be countable.
The language can be infinite, and in fact, all the interesting languages are going to be infinite. But it cannot be uncountably infinite, because a language is a set of sentences, and there are only countably many sentences. Okay. Yeah. So, for example, languages cannot consist of infinitely long sentences, because there are uncountably many such. Yeah.
Is that because the language has a vocabulary here?
No, so the language, yeah, so when you're talking about human languages or formal languages, languages are defined over some set of symbols, right? And you can think of that as a vocabulary. But here we are going to abstract that away. We are not even going to define a set of symbols. We're just going to say that every sentence has some number. So, for example, the sentence 5 may consist of like some sentence in English, right, which consists of many words, etc. Right? But we're just going to call this whole sentence just a number 5. Okay. So this is like slightly different from what we've been doing with LLMs, where we have been defining like individual constituents of sentences. Here we don't care about that. We just say a sentence is just a thing. Okay. Okay. So right, and then next. So now we know what a language is, and then here we have a set of languages, right? So what's a set of languages? So the notation used throughout the paper is you call it like L underline. So a set of languages, which means it's a subset. So maybe I'll write it like this. Is a set of all languages where L is a subset of N. So it's a set of sets of numbers. Okay, that's a family of languages. Okay, and then finally, what does it mean to learn a language? Well, so humans don't just learn one language, right? There isn't a one human language. It's more like there's a whole collection of possible languages, and then you expose a learner to that language, and then the learner learns the language, right? So the language that the learner ends up learning depends on what they were exposed to, right? So we are going to make a few assumptions here. It's kind of entertaining how they talk about this in the paper. So first of all, the assumption is that the language that the learner learns depends on the language that the learner has seen, right? It doesn't depend on anything else. It doesn't depend on hugs, or it doesn't depend on happiness or rewards or anything like that. That's the assumption that we're making in the paper. It just depends on what the learner has seen, right? So what is a learner? And we are also going to assume that the learner doesn't just see some fixed corpus of text and then learns the language. We are going to assume that it's sort of an interactive process, right? So the learner sees a sentence and then maybe thinks of a language in their head, and then sees another sentence and then thinks of another language, etc. Right? So it's going to be like a sequential process where there's like an infinite sequence of sentences that the learner can see. And after it sees every single one of them, the learner hypothesizes what the language could be. Okay? So a learner is a function from lists of sentences. So I guess lists of sentences, let's just remember, sentences are numbers, so lists of sentences are finite sequences of numbers, right? And here I write G. What does G mean? Well, G is a grammar. Okay, so is a grammar. So now this is not going well. I said we would define all these terms, but now I've introduced a new term as part of this definition, right? So what is a grammar? Well, a grammar you can think of as just a set of rules that define a language, right? So like English grammar, traditionally, as you might have learned in school, is, there's structures of sentences and so on, right? We are going to abstract away from all of that. We aren't going to say that a grammar has to have a particular form. We're just going to say that a grammar is a set of rules that defines a language, okay? There might be multiple grammars for a given language. That's totally fine, right? So that's why we're talking about it, not a function from n star to a language, but it's to a grammar, because there could be multiple grammars that define the same language. And as far as the learner is concerned, there might be different grammars that in the end define the same language, but it's going to be useful to talk about these as different grammars, right? So. Okay, and let's take a brief detour now. So this is getting a little bit hand-wavy, right? Like we're trying to do math here. We can't just talk about rules. So we're going to make a certain assumption. And the assumption is basically that the rule for L is something like it's a well-specified program that could run on a Turing machine. Okay, so this is how we are going to sort of bring everything in. So we are going to identify a grammar for language L is a Turing machine right? And if it's a Turing machine, well, what is it going to do, right? You can think of two ways of defining this. One is you could say that it's a Turing machine that takes a sentence and then tells you whether the sentence belongs to that language, right? So I'll write it's a Turing machine M. Maybe I'll write it as MG, right? So corresponding to that grammar. So MG is going to take a sentence as input. So it's a function from inputs, from numbers. And then what's it going to output? Well, if the language is in L, it should accept, right? So it can either output accept. And if the language, if this input is not in the language, then maybe it should reject. So it can reject. And what's the third possibility?
Unknown.
Yeah, it's unknown or it doesn't halt, right? So basically the Turing machine just keeps going forever, right? So I'll write that as 1, okay? And then we'll say that, so actually we won't require that, so we will require that for any sentence that's in the language, the Turing machine halts and accepts. But for any sentence that's not in the language, it could either reject it or just go on forever, right? So these are called recognizable languages. So L is recognizable. If MG of a sentence is accept, if and only if the sentence is in the language, right? And if the sentence is not in the language, you don't do anything. It could reject or not halt or whatever, okay? So that's fine. And there's a sort of basic result in computability theory, which maybe we'll go over if you want me to, which is that equivalently.
What is N?
N is a sentence. So remember here I said all sentences are just numbers. So whenever I write something like this, so you should think of this as a sentence. Right? So every sentence either belongs to the language or doesn't, because the language is a subset of sentences. And then you have a Turing machine that if it belongs to the language will halt and accept. And if it doesn't, it will reject or not halt. Okay? Yeah.
Maybe you're still going to get into this, but when you started defining the learner, you said it's like the sequential thing.
Yeah.
I don't see how that's the case here. And also like this.
We haven't gotten to the learner yet.
Okay.
So we are just still defining that what we consider a language.
I see. And this n star, like, I mean, the language is an element of n star, but it can take in some.
The language is not, no, the language is not an element of n star. A language is a subset of n, which could be infinite, right? So the elements of n star are all finite strings in n.
Sure.
Because that's just like so this string in n, which we'll get to in a minute, is like the first sentence the learner sees, the second sentence, and so on.
Okay, I see.
And so far, after seeing any finite number of sentences, the learner is supposed to output a hypothesis.
Yeah, I understand.
And then keeps going. So, but we're not talking about that yet, we're still talking about all the languages, right? Okay, and then equivalently, so this is, I should have said, if there exists a Turing machine such that this is true, then the language is said to be recognizable. But equivalently, L is enumerable if there exists a Turing machine which well, so this is a different kind of Turing machine. It's not going to be a Turing machine that says yes or no. It's a Turing machine that's attached to a printer. And the Turing machine just prints out all the valid sentences in the language. Okay? So which outputs all sentences in L. And all this means is that if you pick any sentence in the language, then eventually the Turing machine will output it at some point. But the Turing machine might also just output a bunch of duplicates in between, right? So the Turing machine can just, so you turn it on, it starts printing, and then it can print the same sentence multiple times. But any sentence in the language, it will eventually print, okay? So, so it turns out that these two are equivalent. Do people, does this seem surprising, or does anyone not know why this is true?
What's the difference between numerable and countable?
Countable just means that basically it can be put in bijection with natural numbers. It doesn't say anything about a Turing machine, right? It's a property of a set.
Okay.
And here we are saying that this is enumerable by a Turing machine. So this is called effectively enumerable. So yeah, so there's a Turing machine which produces this list of infinite list of languages. Yeah. So should I just to show of hands, how many people want to see like a quick proof that these two things are equivalent? Okay. Okay. I have a bunch of people. Yeah. Okay. So let's go in the easy direction first. So proof of equivalence. So first of all, so let's do the enumerable implies recognizable. So what does this mean? We have a Turing machine that will print out the sentences in the language, and we want to produce a Turing machine that will decide whether a sentence is in the language. So how could we construct, so given enumerator M, we need to produce a recognizer. Let's call this M prime, right? So how are we going to do this? Sorry, yeah.
Oh, you have a Turing machine that simulates the Turing machine that enumerates stuff and also takes as input the thing that you need to recognize.
Yeah.
And then if it eventually outputs that, then it recognizes, otherwise it might never
Right.
stop.
Yeah, exactly. Okay. So does that make sense to everyone? Yeah. So you have a Turing machine that takes, I'll just repeat it, just if people didn't hear. So the idea was that we are going to take a Turing machine that takes a number as input, and then it runs this Turing machine. And then if this Turing machine ever produces that number, you're done. You say that the sentence is in the language. If it doesn't, you just keep going forever. So you never reject a sentence, but you just keep going forever, right? And that's okay because that's all the recognizer needs to do. So this is the easy direction. The next is the hard direction. Well, not really that hard, but okay.
Do you have to do it for all N L? Like, I still have a problem with this recognizable definition.
So the recognizer is given a particular sentence as input, and it just needs to say yes or no whether the sentence is in the language. But it doesn't need to say no. It can also just keep going forever. So it needs to recognize a particular sentence that it is given as input. Right. So remember here, this is the function a recognize. So it's a recognizer that takes a particular sentence as input and then either accepts, rejects, or goes forever.
I see.
Yeah.
Do you have some kind of like result in like a Turing machine can simulate like countably many like Turing machines, something like that?
Here it doesn't need to do that because there is one Turing machine.
Yeah, I'm just curious about that result. Like you have.
Yes, there is such a result. Like basically, what you do is you simulate one step in one Turing machine, then another step in another Turing machine, and then you do this for all Turing machines of increasing lengths.
So you have to have like finite number of Turing machine or countably many.
You can have countably many Turing machines. You just have to order them in some way. But yeah, so yeah.
Kind of don't like the way that the recognizable definition is written. So it kind of seems like there's equivalencies from, it's just because there's an if and only if. Should that just say whenever n is in L, then there exists a Turing machine that,
Yeah, but if and only if is the same as whenever, right?
well, I guess, okay. It could just be me. It's probably me.
I'll just say that if and only if is the same as whenever.
Like from first sight, this definition looks like it depends on n.
If there exists an MGN, I see. If there exists an MG
dot.
Yeah, so I should say there exists an MG such that for all n,
Yeah.
MG of n equals except if and only if n is in L. Is it better?
Yeah.
Is this also
Yeah.
better? Okay. Yeah. Right. So we were working on this reverse direction. So we started the recognizer and we want to come up with an enumerator. Right. So the first thing you could try. is that you could just generate all the sentences in the language one by one, so 1, 2, 3, and so on, and then you could run your recognizer on them, and if the recognizer halts and says yes, then you print that sentence out, right? The problem is that if your recognizer doesn't halt, then you don't know whether that sentence was in the language or not, right? And then you're just stuck, and you just never produce any more sentences, right? So how we solve this problem is, so the algorithm is basically going to be like this. So the idea is basically that when you simulate the recognizer, you don't just let it run forever, you let it run for some finite number of steps. Okay? And if it halts within that finite number of steps, then you know the answer. If it doesn't halt within that finite number of steps, then you don't know, right? So it may or may not be part of the language, right? And then the idea is basically that you will just keep doing this, but for longer and longer number of steps, right? So the algorithm, I'll just write it out in pseudocode. So for, let's call this K, N, 1 to infinity, for N, let's call this not M, but let's say for M equals 1K, and then now for all languages, for N equals 1 M. Can people see this, by the way?
Mm-hmm.
So run user on N for M steps, and then output N if exit. Okay, does this make sense? So all we are doing is, so we are first picking a K, and K will just keep going from 1 to infinity, and then we first pick a number of steps that we are going to simulate the Turing machine. Wait.
Can you just remove the M?
Oh, yeah, we don't need this in here. Let's try this. So N equals 1, 2, K. Yeah. And then we run this for K steps. Yeah. Sorry about that. Yeah. So the idea is first we fix how many steps are going to run the Turing machine, and then we enumerate all the first. So we're going to fix some number, and that number is going to serve two purposes. One is how many steps should I run the Turing machine, and the second is how many sentences should I consider, right? So for example, if I pick K equals 10, then I'm going to consider the first 10 sentences, and then also run the Turing machine for up to 10 steps. Okay, and then I just run the Turing machine on each of the first K sentences for K steps, and if the Turing machine says yes, I print out the sentence. If it says no, then I don't do anything. Or if it doesn't stop within 10 steps or K steps, I still don't do anything, right? And then what's the proof that this algorithm will eventually output every sentence in the language? Yeah.
It enumerates through every single sentence, and it spits out if it's
Yeah.
yeah.
Yeah, so if somebody gives me a sentence, that sentence has some length,
Yeah.
and the Turing machine will output accept eventually for some number. And so I just take the bigger of these two numbers, and whenever K gets that big, then that sentence is going to be in the set of sentences I'm considering, and the Turing machine will halt on that input within K steps. So that's when I will start producing this sentence. And then I will repeat that sentence multiple times after that, but that's okay, right? We are allowed to do that. Alright. Okay, so that's basically the proof. So let's okay, so we've defined everything that we need, I think. So by the way, and then we are going to have some criteria for what does it mean for the learner to learn a language, right? And so this is where there's going to be some room for variation. So on Thursday, Shivam will present an alternative if you don't like what I'm talking about today. But let's start with what I'm talking about today, and then we'll see what happens. Okay, not to spoil too much. So okay, so what we're going to talk about. So let me erase this, right, because people have maybe with this algorithm.
Sorry, in the algorithm, I think it's important to remove the sentences that we have already enumerated.
No, because we explicitly said that enumerator can duplicate sentences. Like it doesn't have to produce every sentence exactly once. And if you don't remove sentences you've already produced, then what the worst that can happen is that you say produce the same sentence multiple times. But that's okay. All we require is that every sentence gets produced eventually. Does that make sense?
See. I should think more.
Yeah, because if you remove sentences you've already seen, that's not changing whether eventually you produce a sentence, right?
Okay.
So if you have a program that does this, you can make another Turing machine that produces sentences without duplicates, and all that does is it keeps track of every sentence it has output, and then it just checks every time it outputs a sentence, it checks whether it's already outputted and if it has. So if you have this enumerator, you can produce a non-duplicating enumerator as well.
Okay.
But we don't need a non-duplicating enumerator. Okay. And in fact, when you're going the other way, in this proof, we didn't assume that it's a non-duplicating enumerator, right? So, okay. So. Okay, so what is the criterion? Oh, and then the last thing is, well, so yeah, so this is kind of obvious, but we are going, so these learners are going to take sequences of sentences, right? So a learner takes, well, input is a sequence of sentences, and this maybe also call it text, right? And so the idea is that okay, so the idea is that we're going to say, let me make sure I get this right. Yeah. So what we eventually want to do is we want to make a learner that can identify. So this is called language identification. We want a learner to identify which language it is from some collection of language, right? So what that means is given L bar or L underline, which is a collection of languages, and then there's some L in the line in this collection, and then P is a text from, maybe I'll call this sigma, so that's what we call it in the paper. So sigma is the text from L, and that just means that all the elements of sigma are in L, right? So sigma I is in L, where all I equal to the length of sigma, right? So it's just a finite set of sentences, and every sentence is coming from L. Okay?
So you can't learn from two different languages?
We'll talk about that in a moment, right? So the idea is that the learner is learning the language, is learning one language based on a text from that language. It doesn't know what the language is, and it has to figure out which language is in that collection based on that one language. But now you could define a collection such that there is some language in it which is a union of two languages, right? So for example, if you grew up in a bilingual household, you might see texts from both of these languages, and then the child might end up learning both of these languages. But then all we'll just say that that's the same as saying that there is some language which is a union of these two languages in my collection, and the child is learning that language, and the texts are coming from both of these languages, right? Because that's what the union of the languages is.
Yeah.
And what are we going to? And then the idea is that actually let's say let's call this T. And so T is actually going to be an infinite sequence of sentences. Okay, so the text is like all the sentences that the child could ever possibly see in their lifetime, but the child is going to see some finite set of finite prefix of this at every time step, right? So
Wait, so T is a set?
T is an infinite list.
Oh, okay.
It's ordered because the sentences are presented in order, which is infinite
Okay.
because like the sentences just keep going on forever. But at every time step, the child has seen some finite prefix of that, and then the child outputs hypothesis.
Wait, how is T an infinite list if it's an n star?
Oh,
Couldn't it just be like a
yeah,
number?
it should not be n star. You're right. It should be n there.
Okay.
Yeah, better. Thanks for catching that. Yeah, so yeah, and so the inputs to the learner are in n star, but
Mhm.
like actually there's an infinite text. Okay.
Yeah.
Yeah. So and then what do we want? So let's see.
Wait, T is a list of sentences.
List of sentences. Yes.
Okay.
Yeah. Which are all the sentences that the child is exposed to one by one.
Mm-hmm.
And then we will say that so the requirements for F identify. So identification is not just for a particular language. Identification is with respect to a class of languages, right? So all the possible languages that the child could learn, right? So what are the requirements? So first, F should halt on every prefix. So I write sigma prefix of, right? So no matter which language, so it's like the environment has picked a particular language, and then the environment has generated an infinite list of sentences in that language, and no matter which prefix of those sentences you give to the learner always halts. Do you have a question?
Yeah, sorry, what is it? F? I might have missed it. F the
Oh,
learner.
sorry. I guess I call this H, right? So it's a learner. So learner H to identify the language. Okay. So I interchange between F and H. The idea is that H is supposed to be the function representing the human learner, but in general you can talk about any learners and we'll call those learners F. Okay. So the first idea is that a child sees a new sentence, and then this child should not just like get stuck and think forever, right? The child should be able to, every time the child sees a new sentence, the child should be able to output a new guess of what the language is, right? This is not saying that the child should halt on all possible sentences, right? It's just that a child must halt on any any list of sentences that are coming from one of the languages that I'm speaking. Right? It's possible that there is some training language that's not in my class of languages, and then if I give the child a collection of sentences, a list of sentences from that language, the learner just goes off forever. That's okay. But we are just requiring that any text that could come from any one of these languages, the learner must halt. So that's the first condition.
Well, that's sigma is a prefix of T.
Yeah. So sigma is a finite prefix of.
Right.
So I should write finite prefix of.
How's it different from just for I in natural number, it holds on Ti for all I?
Because the guess that the learner outputs is not just a function of the last sentence it has seen. It is a function of all the sentences seen so far. Yeah.
Yeah, why is H trying to identify L bar and not L?
Because we are, so the kind of the point of this kind of work is to say, can we say something about a class of natural languages?
Oh, okay.
Right, so identifying a class of languages means that you don't know which language it is in that class, but you're seeing texts from this unknown language and you're trying to figure out which language it is. Right,
What-
like it doesn't make sense to ask what it means to identify a particular language, because then you already know what the language is. Right, there's no game to be played. So this is common in learning theory, right? Like there are many possible environments. There is something unknown about the environment. In this case, what is the language? But you know that the language belongs to some class. And then you are trying to identify which language it is based on the sentences you see. And you know that the sentences are drawn from that language.
So it's not trying to learn the language, it's trying to identify which language is being spoken.
Is there a difference between the two?
I think so.
How?
Like I could hear speech and recognize it as English without understanding what it says or being able to produce English.
Yeah, so that's a good point. So we are not talking about semantics here, right? So when you say learn English, that just means you know what is an English sentence versus what's not an English sentence, right? And you know the difference between, like, for example, you could have English or French. You don't know which one it is. The learner doesn't know, but eventually the learner will figure out whether it's English or whether it's French. And by figuring out whether it's English, that means they will know whether a particular sentence belongs to this English or not, right? So they don't. Yeah, does that make sense? So you can, this set of languages could be infinitely big, right? It need not be English or French. It can be like any possible thing you can think of. You can think of it even as like the configuration of all the possible neurons in your brain that are responsible for producing language. Right? Yeah.
So you're basically saying like a child is exposed to a bunch of languages, but they're trying to identify
A bunch of sentences coming from one language. And that language is one of these things. So think of the world as choosing a particular language,
Okay.
producing texts from that language, and then giving them to the child. So for example, all the people around the child, let's say they all speak the same language, right? They have chosen some language. The child doesn't know what language that is, but they have chosen it. And they are giving you sentences in that language. And then eventually the child should be able to figure out what language everyone around them is speaking, by which that means that the child should be able to tell for any other sentence whether that sentence belongs to a language or not.
I feel like maybe I'm misunderstanding, but I think the confusion is that people are thinking that you need to learn all the languages in the set L_bar.
Yeah.
But this notation of identify L, I guess, is the same as when you say you can learn a hypothesis class.
Yeah.
In the sense that, like,
Yeah.
what it means is that if you're given any language in this set, you can learn it, or you
Yes.
can identify it.
Yes, so
It's
that's
not that
so this is a conflict between the learning theory usage of the word learn versus sort of the common English usage of the word learn. When I say I'm learning a language, that means I'm like, what it actually means, like mathematically you're looking at it, is there's like an infinite family of possible languages, and I'm figuring out which language in that set I've been exposed to, right? So learning a language or learning a class of hypotheses is the same as identifying which hypothesis in the class is the one that you're being exposed to. There was some question over here as well. Not anymore. Okay. Did that make sense?
But why would you need the learner to take a list of sentences as an input?
Because you're thinking of it as a function, right? So so when you have a function and you're producing some output, in this case it's identifying a language, it can only depend on the input, right? Like the function's output only depends on the input. And of course the guess that a learner has, in this case a child, depends on the entire history of sentences that they have seen, right? So it needs to be a function from a list of sentences. Like you cannot learn or you cannot identify a language based on one sentence. Right?
Well, what if, like, for all sentences in this list, you can identify instead of a list? Like, I just don't see the difference.
You mean the difference between a list and a set? Or I'm not sure I follow.
It's like you're saying for all prefix. I think it's more complicated than for all sentences in this list. Like you don't have to.
It's not for all sentences in the list, it's for all prefixes of the list. Right, so let me, how should I, so imagine this, right? So imagine that I have a set of sentences, which I will say like S1, S2, and so on, an infinite list, right? So on time step 1, the learner sees S1, and then it produces some grammar G1,
Yeah.
okay? On time step 2, the learner sees S1 and S2 and produces G2.
Why not just S2?
Because the grammar it produces here will also depend on the first sentence, right? So when I say, if I write a function, f of S2 is equal to G2, so this can't work because actually it needs to be f of S1 and S2 equals G2, right? This is the guess that the learner produces after seeing both of these sentences.
Oh, I see. Okay.
Right?
I see.
Okay.
Sorry.
Yeah.
Sorry again about the learning. I think what I understood is that here the label set is L underline itself, and given some sequence of sentences, I should figure out which L is
Yeah,
these sequences are coming
Yeah.
from,
that's right.
which is kind of different from the grammar that we have in the corner. What is the grammar there?
So the
And-
grammar is, when we talk about the grammar, we're saying what is this G2? Because, so there we're talking about the output side, right? So when I say that a learner has identified a language, what does that mean? It means that the learner has a rule in their heads.
Okay,
that
the
allows them to
hypothesis
figure-
is the grammar.
Yeah, the output is the grammar. So
Yeah,
you can,
I
you-
see.
You can think of that as a rule that allows the learner to figure out whether any sentence is in the language or not.
Yeah, but the label set is L underline.
Exactly, yeah.
Okay.
Yeah.
And it's different from the, for example, the way that we call learning is, for example, having some mapping from one language to another language.
Well, that would
It
be
has some.
translation, right?
What was that?
That would be translation,
Yeah, that would kind of translation.
right?
But this is, we are kind of language identifier here.
Yes, we
kind
are a
of.
language identifier.
Okay,
So
cool.
this, in particular, this is not talking about semantics, like I said.
I
Right?
see.
So for example, if you had like somebody who could like perfectly produce every sentence in English, but didn't know the meaning of any of those sentences, that would still fit this
I see.
definition.
Yeah.
And we are almost, well, this is kind of what LLMs do, right? Like if you have an LLM that can perfectly produce only the sentences in English and all the sentences in English, but never produces any sentences that are not in English, then you could imagine that LLM kind of learned English, right? Even though it doesn't know the meaning of it,
Yeah.
right? So meaning is not an externally observable thing, right? A meaning is something else, right? So we're not talking about that here. Yeah, so does this make sense? Why the learner is a function from all prefixes, so all finite prefixes to grammars. So, and you can think of the grammar as basically a Turing machine, right? So the learner is producing a Turing machine, or producing a set of rules that will then be able to evaluate whether some sentence is in that language or not, right?
So like, for example, like Spanish and Italian share certain phrases.
Yeah.
So by seeing like S1 being their shared phrase, I don't know if it's Spanish or Italian. Then for the second sentence, it's only from Italian, so I know it's Italian. That's why we need to take a list of sentences into input.
Well, I would also just take in, like, for example, like if, so remember, a grammar is a Turing machine. This is one sentence. Can you produce a Turing machine that recognizes English from seeing one sentence in English? So we don't even need two languages, right? Like, if English is a big language, it has lots of sentences in it. Can you hope to produce a Turing machine that can recognize English sentences from seeing one sentence in English? Of course you can't, right? So you have to see a collection of sentences. And then you can decide, you may be able to generalize from that and say, okay, I've seen some finite collection of sentences. From that, let me try to come up with some rule that generalizes what I think all these sentences have in common. Yep.
If it's only seeing sentences from one language, wouldn't it just think everything comes from that language?
But it has to figure out which language it is. So for example, let's say there are two languages and one is a superset of the other, right? And now it has seen sentences coming from the first language. Should it then decide that it's the first language it has seen or a second language? Like what it has seen is not inconsistent with those, right? So that actually, so let me move on. So that will get at kind of what the goal is, right? So right, so let's continue this list of requirements. So the second thing is that H should output grammar for L all but finitely many times. Right? So what this means is that after seeing every sentence, the learner is outputting a guess for this language, outputting a grammar, and eventually it should stop making mistakes. Right? So there should be some time point after which the learner has picked the correct language from this class, and then after that it never picks the wrong language again. Right? The learner doesn't have to know that it has done this, right? So the learner, so this is called convergence, right? The learner eventually converges on the right language, but we don't know like how long it takes to converge, and the learner itself may not know that it has converged. Okay? So the idea is that eventually a child will learn the language, but there is always a possibility that no matter how much you think you learn the language, you see a new sentence that's not in the language, right? And now you have to change your mind, right? So that's totally fine. But if the text is coming from the language, then you will never ever see some sentence that's not in the language, right? So the idea is that, so if the text is coming from a language, first the learner will never see a sentence that's not in the language, but we also require the learner to eventually realize that it is that language, that it's not some other language. And then it should never make a mistake after that. Okay? Seem okay? Alright?
Should it be a grammar for L bar or?
A grammar is a rule for a particular language.
Oh, okay.
Right? So this is saying it's, and there could be multiple different grammars for the same language, and a learner could like switch between these grammars, but they should all be for the same language.
Okay.
Can I just feel like there's still this confusion about what identify means here, and maybe I missed, but I think the reason these questions are being asked is because like saying that a learner identifies a set of languages, right, is really saying that like for all languages in the set of languages, the learner will actually output that language.
Yeah.
Right?
So we need a for all here.
And that's what identifying means.
Yes. That's what identifying.
Yes. The point is that I think there's, like even the question I just heard, it seems like there's confusion that we're learning the set of languages as opposed to learning the language in it.
Right.
But that's just a matter of how we're
So
interpreting the word
actually,
identify.
so the language is kind of unfortunate because people do talk about identifying a language and identifying a set of languages. Let me just say that identifying a language means if you're given a text from the language, eventually you will start outputting the grammar corresponding to that language and you will start making mistakes. And identifying a set of languages means you identify every particular language in that set. And what that means doesn't mean that in any particular environment or like any particular environment is just one language, right? But it means that hypothetically you could be in any of these different environments, which all correspond to different languages, and then you would identify whichever language that environment is, right? So the child is never called upon to learn all the languages in the set, right? The child is called upon to learn one language, and by which we mean the child should figure out which language in the set the text is coming from. And the text is always just coming from one language, right? So if you want to think of it as a game, imagine that I'm the adversary or the environment. It's not an, so let's say I'm the environment, and there is a child, and there is some possible set of languages. We both know what that set is. The child knows, well, may not know consciously, but somewhere in your brain it's encoded what the set of languages is, and the environment knows what the set of languages is. This is before everything happens. Then when the game starts, I pick one language, I produce an infinite set of sentences from that language, and I present them to the learner one by one. And this learner has to eventually figure out which secret language I picked. And that's what this convergence is. If I now want to pick a different language, well, now that's a different game, right? So now if I want to start over, that's like a totally different universe in which there's a different language, etc. So we are not talking about acquisition of multiple languages, we're talking about the first language that the child learns.
So it has to identify which language it also has responding in the right grammar or the language itself.
If you want to talk about responding, you should come to Shivam's talk the day after tomorrow. But here we're just talking about identification. So we are not asking the child to ever produce any sentences in the language. We are asking the child to produce a grammar for that language. But of course that is stronger, because the child can produce a grammar for the language, then the child can also produce any sentences in that language, because you have a machine that generates them. Yeah. So yes, so this is stronger than talking in the language. Yeah.
So then, I guess in the requirement too, we're just missing like for all L in L underscore, right? That's what you meant.
Yes. Yeah. So I put the for all L up here, so that that holds for all these requirements. So yeah. So all of these requirements have to hold for every language in that class. Okay. Yeah, and then the third requirement. Well, it's not. Yeah. So. Yeah, and so I won't write all the rest down, but it's a vocabulary, right? So basically saying that when I said what it means to identify a language, that means that if I'm given a sequence of sentences from that language, eventually I'll figure out which language it is. and identifying a class of languages means that I can identify every language in the class. Right? So that's just all this vocabulary. Yeah, and then we will say that a class of languages, I'll write this down. So we will say that, so a class of languages identifiable if some learner identified it. So let me unpack this a little bit more just to avoid confusion. So when you talk about learning a language, you cannot talk about it, like even though I'm saying that there is one language that the learner sees, it's still important to talk about what the possible languages are, right? So for example, like somebody was saying that Spanish and French are very similar, right? So if both Spanish and French are in my set of languages, then it might be hard for me to identify this set because they're quite similar, right? So I'll have to I might see sentences that could plausibly be in both languages, and so I might have to do a lot of work to figure out which language it is. But if the set of languages I'm talking about only contains, let's say, German and Spanish, which are quite different languages, then it might be much easier for me to identify Spanish, right? So even though in both cases I'm given texts from Spanish, in one case, the other possibility is that the text could have been from German, and in the other case, the other possibility is that the text could have been from French, right? So yeah, so does that make sense? The hardness of identifying the language depends on the class of languages, even though you never see anything else in that class, right? Because it always matters like what the possible wrong answers are, not just like what the right answer is. Does this sound okay? Lots of nods. Okay. So that's why another reason to talk about whether a learner can identify a class of languages. It doesn't really make sense to talk about identifying a language without talking about the class of languages that the learner is considering. Right? And this is why when we started out, we said that we want to be able to say some things about the class of all natural languages. Right? So we are not going to say particular things about particular natural languages like English or French or German or whatever. We want to say some universal things about the class of all natural languages, which we define as a class of languages that a human child could potentially figure out. Right? Okay. So okay, so this is all. So let's get to our first result of this type, right? What can we say about the class of natural languages if we are assuming that humans can identify particular languages in that class based on seeing sentences, right? And so this is a result that's from Gold. So so Gold's paper talks about whether or not this problem is solvable, right? So if you fix some collection of languages, is there a learner that can identify languages from that collection, right? So, and this is based on various assumptions on the set of languages and various assumptions about the learner, right? So let's see that. So, so there's a weakness. And spoiler, most of these are negative results. Most of these results are going to say that for any interesting collection of languages, you cannot identify them, right? So there is a whole bunch of these results. Let me just give one of them. So this is called the weakness of text, because the rule here was that I'm given a bunch of sentences from the language. That's all the learner has to go on, right? The learner never sees negative sentences. So it never sees sentences where somebody tells it this sentence is not in the language, right? So that is one weakness. You are forced to learn a language just from positive examples. You never see any negative examples where somebody tells you that this is not in my language, right? And then it turns out that if L bar, so this is a collection of languages, has all finite languages and one infinite language, then L bar is not learnable. So what is a finite language? It's just a finite subset of sentences. What's an infinite language? Well, it's an infinite subset of sentences. And if I have a class of languages that contains all the possible finite languages and one infinite language, then you can't learn it. Yeah.
I guess the L bar is the same as that L bar with the bar underneath you wrote, right?
Oh, yeah, yeah.
And then learnable means identifiable?
Yeah, thanks for catching all of these things. Yeah. Yeah, I have like this tendency to always confuse when people use learnable and identifiable interchangeably. But yeah, I'll try to say identifiable every single time. Okay. So yeah, so what is the significance of this result? Well, the idea is that like we think of natural languages like English, for example, is an infinite language, right? Like there is no finite set of sentences that belong to English, right? You can make up lots of English sentences, an infinite number of them, right? And the idea here is that if my class of natural languages contained English, but it also contained all the finite languages. The finite languages are just languages which if they have a finite set of sentences, but you can also think of that as the sentences can't be infinitely long. And yeah, so there is basically some, like it's some finite subset of the natural numbers, right? So think of it as all the numbers less than 10, that's one subset, finite. All the numbers less than 11, that's another subset. So imagine that you have a collection of languages that just contains all of these finite subsets, but also contains an infinite subset. Then this is not learnable. Yeah.
But aren't all languages kind of these finite subsets? Like no one's writing a sentence that's longer than like 100 words, right? And then you only have a finite vocabulary, so
right.
Like I mean, in theory, you could make a sentence very long, but like you're never gonna do that. Right?
Yeah, but there is no rule in English that says that as soon as the sentence becomes longer than 100 words, it's no longer English.
Yeah.
Right. So.
I agree.
So grammars, right? Where have your grammars of like eliminating some of these like infinitely long sentences?
So okay, let me put it differently. I'm not saying there are infinitely long sentences. I'm saying that there is no upper bound on how long sentences can be. Right? So if you had a finite set of sentences, then there would be some longest sentence in this set. And you can look at the length of the longest sentence, and then you can say every sentence is shorter than this. But in English, is there like a rule that says that no sentence can be longer than 100 words, 200 words? Of course there isn't. That doesn't mean there are infinitely long sentences. It just means that you cannot come up with a number and say that all sentences are shorter than this.
But I guess what I mean is maybe we should be okay with this.
Yeah.
For that reason. Like.
Yeah.
But I still don't entirely understand what I meant by infinite language and one infinite language. Do you mean?
So the example could be, for example, like imagine the language that contains all the multiples of the number 10. This is an infinite language because it contains an infinite number of numbers. Yeah.
Is there a concept of making a mistake while learning a grammar in this? Because all you are being exposed is to a particular language. Then is there really making a concept of making a mistake while identifying that language?
Yeah, so that's actually what was covered here. Should output a grammar for L all but finitely many times. So the learner is allowed to make mistakes. It just cannot make infinitely many mistakes. So what this is saying is that if you keep giving the learner more and more sentences from the language, eventually the learner will figure out which language it is. But before then, it can just keep making mistakes. Right? Like, it's like you don't look convinced.
I understand that the learner knows that there's a set of languages among which one of those languages sentences are being exposed to it.
Right.
So when there's only one language that is being exposed to it, then there are no negatives.
Yes.
Then how is it really making a mistake? It is simply learning to make the grammar more and more robust in understanding and in identifying that particular language. Right. Isn't mistake still a wrong word here?
Yeah, so mistake is not something the learner knows. Like, so the mistake is a concept that we can see from above, right? If you're looking at a child learning a language, like we know, if you're the environment, we know what the right language is. And if the child ever guesses a grammar that's not that language that we know, then we call that a mistake. But the child can never know whether it's a mistake or not.
Okay. So a question about the setup. So when we have this infinite ordered list, do we get the label of the language?
So the infinite ordered list was just had nothing to do with particular languages. This was just a convenience to say that every possible sentence in every language can be represented by a number.
Yeah, but the setup was like the learner observes this infinite list.
The learner always observes the finite prefix of the infinite list.
The finite prefix, but does he observe the label of which language this text belongs to?
No, and so first of all, every sentence belongs to the same language, but the learner doesn't know which language that is.
So he just, like, this is some prefixes from one language?
Prefixes from one language. So the text need not be the language, right? So the text is just some infinite collection of sentences, and the only requirement is that every sentence shows up somewhere in the text.
Okay.
But they need not show up in any particular order. Multiple sentences could show up, whatever, right? So regardless of which text, so there are many different texts that correspond to a language. And intuitively, right, like if you're learning, you grow up in an English-speaking household, I mean, you're going to be exposed to lots and lots of English sentences, but like nobody has any idea of which sentence in particular, etc. You're just assuming that every English sentence will eventually show up. Yeah. Did that answer your question?
Yeah.
So let's say that there are two sentences that in a representation space are pretty far from each other. And the first sentence is exposed to the learner, and the learner identifies it as an English sentence. Let's say we are talking about English. The second sentence is relatively very different, as it's very far in that representation space, and it is not able to understand if that is from English or no, from the space, from the same language or no,
Right.
and updates its grammar accordingly. So is this kind of a mistake?
So if the updated grammar corresponded to the true language that both these sentences are from, then it's not a mistake.
Okay.
If it didn't, if it was like some grammar, then that is a mistake. So whether the learner made a mistake depends not on like anything else, it just depends on which grammar it output. So, and what does it mean for a grammar to be wrong? It means that it will wrongly accept some sentence that's not in the language. Or it will like wrongly reject the sentence that's not in the language or whatever, right? Like we have talked about what the grammar is.
Right. So the grammar is not evolved enough to understand that if that's an advanced sentence, it's part of it or
Yeah,
no. Okay.
right. And we will weaken some of these assumptions later on. Maybe we don't have much time, but we will. Yeah, so I'll try to get, maybe I'll try to pick some of these important things. So, okay, so let me just give you some results. So this result, I was going to give a proof for this, but we don't have time. So, but basically the idea is that you can construct an infinite set of sentences that all come from this infinite language, but you can force the learner to pick one of the finite languages and then keep switching between them infinitely on. So so basically the idea is to construct a sequence of sentences that all come from this infinite language, which is the infinite language. But then the idea is that you repeat the first some number of these sentences multiple times until the learner decides it's coming from a finite language. And the learner will always do this. And then as soon as the learner has said this language, and then you switch to showing it a new sentence. So that this kind of ties into your idea, right? So you're kind of saying that you can force a learner to just keep on making mistakes forever by giving it more and more sentences from the infinite language, but then waiting until it decides that it must come from the finite language.
Mm-hmm.
And so you will just keep on making mistakes forever. You will never ever decide that you actually are seeing sentences from the infinite language. That's basically the idea of this proof. And the reason you can do this is because the adversary, because here we're trying to make a statement about all possible texts, and that text can be chosen to sort of to highlight weaknesses in the learner, right? So if you know that if you give a learner a particular, like you can simulate the learner, right? You can say that, okay, if I give the learner a billion sentences that all come from this finite language, then eventually the learner will say it is that finite language. It is that finite language, and you know when this happens. And so the next sentence you can make it come from a different language, and then you just keep on doing this, and so you can show that the learner will never figure out that it's coming from an infinite language. Okay, so so that's the first result. Let me pick which other results I want to talk about. Okay, and so so now one of let's see. Yeah, and then we might want to put some restrictions on the learner. So right now we only put restrictions on what the language is, right? So we said that the language has to have a Turing machine that can decide whether something is in the language, so a recognizer. but should we also put restrictions on the learner? Right? So right now we've just said that the learner is just some function, function from n star to g, but you could require that the learner is also a computable function. Right? So whatever algorithm is running inside the child's head could be expressed in some Turing machine. Right? So that would be assuming that the learner is computable. And if you're assuming the learner is computable, then that puts certain restrictions on what we think of as natural languages. Right? So if we are assuming that the natural languages are the set of languages that can be identified by a learner, and the learner is a particular kind of function, like a computable function, then that puts restrictions on what the natural languages can be, right? So that could be one.
So the natural languages definitely can't have one infinite language in it, because if they did, then
it
even
cannot
the
have
learner,
an infinite language and all the finite languages. Yeah, that's the
Okay.
beauty. And we're kind of saying that actually what this means to say that we know that there are infinite languages in the set of natural languages, which means it cannot have all finite languages.
Mm.
So there must be some finite sentences that are just not part of any natural language.
Mm-hmm.
Yeah.
I don't get that last conclusion where you say there must be finite sentences that are not part of any natural language. Like, couldn't you have a lot of infinite languages? And couldn't you have one infinite language and have any finite sentence
Yeah,
related
yeah,
to that
yeah.
one infinite language?
Right. So here we are not we are arguing in opposite direction. We are assuming that the set of natural languages is identifiable,
Okay.
which means it cannot be this, right?
Yeah.
But that means if it contains at least one infinite language,
It can't have all the finite.
it cannot have all finite languages. But if you are saying it cannot have all finite languages, that means there must be at least one finite language that's not in this set.
Yes.
So there is at least one finite language, which is some finite collection of sentences, which is not a natural language.
Sure. Yeah.
So that's all it's saying.
Okay. But it could be a subset of the bigger infinite language, right?
No, if it is a finite subset, it can't. So if you construct a finite subset of English, that's just a different language, right? That just happens to be a subset of English. So here we are not saying anything about whether these finite languages are subsets of L or not. We're just saying that it just cannot contain all finite languages.
Okay.
So it cannot contain, right. Yeah. So it is possible for it to contain all but some number of there's some finite language that can't be in the set of natural languages. That's all we're saying. So it's not really that strong, right? It's just like a result to give a flavor of these kinds of results. Okay, so restrictions on learning functions. So the idea is that if you assume that a learner is a computable function, not just any function, is this an interesting restriction, right? It might be the case that you can make this assumption and it doesn't tell you anything about the set of natural languages, right? Happily, that's not true. So the first proposition says, some proposition that says L bar, so there exists a collection of languages, so there exists L bar such that L bar is identifiable but not by any computable learner. Okay. So another way of thinking about this is that if I assume my learner is computable, then that is actually meaningfully reducing what the set of natural languages can be. Right? It's because there are collections of languages that are identifiable but not by a computable learner. So it's kind of an interesting assumption because at least it's changing the set of what a natural language could be. Right? And then so that's computability. Another possibility is called non-triviality. So grammar is called trivial if it generates only a finite set of, it's a finite subset of languages, right? So earlier we said that any natural language is probably non-trivial in the sense that it has an infinite set of sentences in it. So a trivial language is just one that has a finite set of sentences in it. So finite language, right? And a non-trivial learner is one that never outputs a trivial language as a guess. Okay, so you can imagine a learner that just sees some number of sentences and then just says, well, those are the sentences in my language. Nothing else apart from that, right? So what that learner has done is it has, at every step, it has produced a trivial language, which just contains a finite set of sentences, right? And we want to rule that out, right? We want to say that that children always have rules, that the rules that they're hypothesizing allow for infinitely many sentences. They never produce like a trivial grammar which would just match like a finite language, right? And it turns out that that's an assumption we could make, right? And that also meaningfully reduces the set of possible natural languages. So maybe the first one is any computable learner, any non-trivial learner. So just to make it clear, this exists is not the same for both of these, right? So I can construct a family of languages that is identifiable. So there exists a family of languages identifiable by a computable learner but not a non-trivial learner. Does that make sense? By non-trivial learner, I mean a learner that ever produces a guess of a grammar that only fits finite languages. Yeah.
So I guess if you can show that the computable learner can recognize a set of languages that has one infinite language in it, then this would satisfy this, because then the trivial learner couldn't recognize that or identify that. Like what I mean is I'm still confused why we would force this restriction on the learner.
So just to be clear, I'm not saying we should force this restriction. Yeah. I'm saying that if we were to make this assumption, that would meaningfully change the class of languages that we're considering.
Yeah, but I guess it's like the way I interpret it is it's basically saying like the learner can't learn infinite languages.
I don't think that is true.
Why not? Like if it's not allowed to produce a grammar that can produce infinite languages.
No, that only produces finite languages.
It's only allowed to produce those types of grammar, which
means
it can't produce a grammar for an infinite language, which means it can't.
No, it can only produce grammars for infinite languages.
Oh.
That's what non-trivial means. A trivial learner would be a learner that produces a grammar for a finite language at some point. So those are two simple learners. Here we are saying the learner has to have some level of complexity, you could say, in that it is always forced to produce grammars for infinite languages.
Oh, right.
So that actually rules out this case. Because here we wanted to construct a class of languages that has a bunch of finite languages in it. But here, the learner is not allowed to produce grammars for finite languages, which means a learner like this could never identify a set like this that contains finite languages.
Yeah, that's kind of weird, isn't it?
I think it's natural, right? So this is kind of a weird set. And we want to say, let's imagine that the set of natural languages can't be of this form, right?
Okay.
And then if you know that the set of natural languages, well, even stronger than that, we just say that there is no natural language which is finite. And then we can require a natural language learner to only produce grammars for infinite languages. And then we have to assume then that the languages that you're giving to it are made of only infinite languages.
Yeah.
Because otherwise we'd have no hope of identifying them. That makes sense?
Yeah, I agree. That's good. Thanks.
Yeah. And then there's another one called conservatism, which is basically saying that, so there's another proposition like this, so there exists a language identified by a computable learner, but not a conservative learner. And what this means is that, so a conservative learner is a learner that only changes its guess when it sees a language that didn't fit its previous guess. Okay, so the learner has seen some set of sentences, produced a grammar, and now it sees a new sentence, and if the new sentence fits that old grammar, it just keeps the old grammar. It will only ever change the grammar if it sees a sentence that doesn't fit the old grammar. Makes sense, right? So this is another possible restriction you can make on make on learners. And the idea is that also meaningfully reduces the set of languages that you are considering. So there exist classes of languages that cannot be identified by a conservative learner, but can be identified by a computable learner. Okay. So yeah, so these are just, so let me quickly wrap up. Okay, so I won't get to there's this other idea that people have called strong nativity. Strong nativity just means that the set of all possible natural languages is finite, which is very weird. But the original reasoning comes from like Noam Chomsky and some other people, and they basically argue that a human has a finite brain capacity, right? Only so many neurons and so many different possible things that this computational resources, and so this implies that the set of possible languages is finite, cannot be infinite. It could be a very large set, but it's a finite set. And many people don't quite agree with this idea about limited resources. So the paper tries to take a different tack and say, can you prove that a set of natural languages must be finite? And you can do that if you make certain assumptions, again, on the learner and the set of natural languages. So that would say that if you agree with these assumptions, then you must also agree that a set of natural languages is finite. So that's like a different take on this. Yeah.
Can't you also just put a constraint on time because we can't live forever? So then you can't learn.
Yeah, that would be another kind of that would be another reason to argue that the set of things is finite. Or the Turing machine has limited resources, right? So the Turing machine can only run for this long.
Okay.
That would be a similar kind of restriction. But then the idea is that can you come to this conclusion based on these assumptions? And so the paper talks about some assumptions. But I won't talk about that because we only have like 10 minutes left. Instead, I want to talk about like slightly different thing which covers some of the things you're thinking of, which is that this model seems way too strong, right? Like we are saying, for example, that if the learner wants to identify natural language, the learner is given always sentences from that language, right? Like for example, what if the learner once hears a sentence that is non-grammatical, right? Does that mean the learner can forever like give up hope of like learning the language? Of course not, right? That's too strong an assumption. So these are all these are all variations on this idea of what the requirements are, right? So can we loosen the requirements in some way? Yeah, and so let me write this over here. So the first, alternative environments. And again, I just quickly list what they are. So one is noisy texts. And now the sentences drawn from L union D, where D is finite. Right, so the idea is that, let's imagine that there is somebody in the child's environment who always says like something that's not grammatically correct, right? And they only say a finite number of such sentences. And so you might think that the child can just figure out that these are not grammatically correct and still learn the language, right? So we are still requiring that text will eventually contain all the sentences from L, but we are also saying that the text can contain some sentences, maybe finite, maybe infinite, from D, but there are not infinitely many such sentences, right? So you can think of D as like an alternative finite language, and your text is containing sentences from either of these languages, but you still require that the text will eventually contain all the sentences from L. And can you still learn? Like, can you still figure out what L is, even with this sort of text? And then it turns out, so the proposition says that, so this is actually very strong. So this is saying it exists a collection of languages such that every language in this is infinite for all L in L bar. L is infinite. And any two pairs of languages at this joint, so this is really, really strong, right? So you can, so if you ever see a sentence, that sentence can never belong to two languages from this class. So this confusion problem is gone, right? L prime in L bar are disjoint. But L bar is and I guess this is an and. L bar is identifiable from text, which means like correct text, but not noisy text. Okay, so just the presence of a single like source of noise, which can only contain finitely many sentences, can destroy your hopes of learning from this class of otherwise very easy to learn languages. Right? Without this noise, this would be trivial to learn. You see one sentence, and you know which language it belongs to, because all these languages are disjoint. Right?
Mm-hmm.
But as soon as you add the possibility of noisy text, then that goes away. You cannot learn it by a computable function. Wait, is that a computable function? Yeah, so this should be identifiable by a computable function. Okay, so that's the first negative result. And then the second one is incomplete text.
And it's the fact that a computable function can't solve it from noisy text, or it's even non-computable can't solve it?
So as far as I know, this result applies to computable functions.
Okay. It would be
I
even
think a
stronger, right?
non-computable function should be able to do it.
Okay.
Or at least it's not known. I don't know.
Yeah. That would be really strong, right?
Yeah.
Because D could always be from one of those infinite languages.
Yeah, and this is similar, but the text comes from L minus D. So there are, and again, D is finite. So there are some sentences that you're just never going to see, no matter how long you wait, but only finitely many such sentences. So that's incomplete text, right? And there's a similar proposition that says that there is a collection of languages where every language is infinite, right? Why are we saying every language is infinite? Because it just rules out that kind of nonsense, right? We don't want to worry about that. So we're constructing these sets of languages where every language is infinite, every pair of languages is disjoint, but if you are given incomplete text, you won't be able to identify which language in the set you're talking about. I won't write the proposition out, it's basically the same as this, just replace incomplete, just noisy with incomplete. And then you could have, yeah, so, yeah.
Question.
Mhm.
I know that you have assumption about it being infinite, just trying to rule that condition. But what if you just assume if it's all finite? Like, does any of these results?
Doesn't it
So these are strong results, right? So assuming that it's infinite is making the result even stronger, because it's saying that it's like a hard class of languages that satisfy this property, right? Like, of course, an easy class could.
Easier, like weaker results, but with computable functions.
Yeah, so you don't need like yeah.
Weaker assumptions, like.
So this is not a so this is not making an assumption. It's constructing a set of
The
languages.
assumption of that proposition is saying this is a much harder assumptions, right? Like it's always the infinite.
No, this is not an assumption. This is a claim that the proposition is making. It's saying that exists such a thing. If it was saying for all L something, then that would be the requirement. But this is saying I can show you a set of languages, which is very hard.
I got you.
Yeah. You're asking something?
I was just gonna say, I thought in the finite case is almost, isn't it actually just hard and obvious? Because
yeah,
then
it's
D
obvious.
could just be the language
Exactly,
itself.
because if L is finite and D is finite, then
Yeah.
like you might not see any sentences from the language. Yeah, that just rules out that kind of
Yeah.
non-triviality.
Yeah.
So like if L and D are both finite, then a noisy text can be anything,
Mm-hmm.
right?
Yes.
It's only interesting in a situation where L is infinite and D is finite.
Mm-hmm.
Yeah.
I agree.
Okay. Yeah, and then the last thing I'll say is there's this idea called exact identifiability. So the idea is that so the idea is that imagine that, so what did we define a natural language as, right? We said a natural language is the collection of languages where a learner could identify one of those languages from seeing the text, right? So what would be a non-natural language? Well, it would be a language that doesn't belong to this set, right? Which means that if you add it to the set, the learner cannot identify the set, right? So we will say that L bar is exactly identifiable if no superset of L bar is identifiable, but L bar is identifiable. So, okay. So we are just saying that, like, since we are talking about a class of natural languages, and if you are claiming that anything not in this class is not a natural language, then that means that if you add that thing to the class, then you couldn't identify the class, right? That's effective. So the set of natural languages has to be an exactly identifiable set, right? Like you can't construct supersets of it that are also identifiable, because if you could, then that extra language that you added in would also be a natural language.
And there exists such a set?
So that's the first condition, that there exists such a set. And in fact, that is actually the main result from this, is that for any number, you can construct an exact set that has at least that many elements in it. So you can construct sets of exact languages that are arbitrarily big.
That's nice.
Or exact sets, not sets of exact languages. Yeah.
But yeah, they clearly aren't supersets of each other.
Right. Oh, actually, there's another result, which is, what is this? Yeah, there's a, so it turns out also, so that is one thing, but the other thing is that does this actually give us a restriction? Does this meaningfully restrict what the set of natural languages has to be?
Mm-hmm.
And in fact, it does. It turns out that this stuff, okay, this is 5 o'clock, but this is like the last thing I mentioned, which is that there are uncountably many collections or identifiable collections of languages and here these are computably identifiable. So, but countably many that are exactly identifiable. So if you're just thinking about, okay, I've got a set of natural languages, what could this set possibly be? Well, it turns out there's like uncountably many possible subsets that you could be thinking of. But if I say that this collection of languages is exactly identifiable, then that immediately drops me down to a countable collection of possible languages, natural languages.
Can't you go like the other? It's like if you knew the second result, which is there's countably many, then from that you can just take any subset and you get the uncountably many or something. No?
I don't know if it is true. Actually, no. So subsets of those sets will not be exact, right? Is that?
Yeah, that's what I mean. They'll just be identifiable, but they won't be exact. And it's like what is it, like 2n to the n is uncountable or something? I don't know.
Yeah. Oh yeah. I think that works. Yeah. So if you have like countably infinitely many exactly identifiable things, and then you take subsets of them, then you get uncountably many languages, and none of them are exact because they're all subsets of some other exact set. Yep, that works. And so I guess the main part of the result is saying that there are countably many exactly identifiable sets.
Yeah.
It's always true that there's more of these than there are of these. Yeah.
That's interesting.
Yeah. Okay, so I'll stop there. If this whet your appetite, read the paper, and Shivam will talk about some fundamental issues with all of this stuff. So have fun. Yes, thank you.